Okay, it's my pleasure to introduce one of our alum. He worked for Stuart Smith, Herman Sobelaga Gomez. He's as the title says, the global product manager for Zeiss Group. And we also have a Zeiss local leader, Amy.
All right, thank you, Professor Raha, for the kind invitation. I'm really happy to be back here, a place where once, over 10 years ago, I was a student too, just like you. So it's a pleasure to be back. I'm going to talk about X-ray computer tomography for dimensional metrology and non-destructive inspection. So let me take a little bit on my journey. I currently work for Zeiss. I've been with the company already for 6 years. I'm a global product manager, and for those of you that might wonder what a product manager does, my function is basically to look at the portfolio we have. In this case, my product portfolio is X-ray microscopy, and then to see if there are any gaps or any needs from the market. I'm responsible of bringing those feedback from real customers to the R&D department for new developments we want to do in the next 2 to 3 years or so. So kind of have a long-term vision. And I also get involved once the R&D develops the product with good feedback from the market. I'm responsible for that product launch. So I get heavily involved in marketing, in shaping the technical messaging for the customers to see what we have, what is this product about. And once we launch the product, we also have, I personally have to support with my technical expertise the sales staff. When customers call or they want to talk to very deeply, a very high technical level of what this kind of product is, what the measurements are, or what the type of data they're gonna get from it, if it is the right fit for their needs, then I get involved. So it's kind of fun. It's an intersection between product development, marketing, and sales. And because it is a global position, I get to travel around the world, which is kind of nice too. Before that, I was with Nikon Metrology. I was also in the X-ray CT business. I was an application engineer, so basically responsible for doing demonstrations, talking to customers, and often ongoing also to conferences and talk in trade shows. And before that, I actually was an intern for Zeiss back in time, 10 years ago, for 1 year. After being here at UNCC for 2 years, I went to Zeiss for one long 1 year internship where I was actually measuring parts, all kind of parts from all the sectors, automotive, electronics, medical, with X-ray computer tomography. And I studied here at UNCC. I did my PhD here. My time here was actually short-lived. I only spent here a couple of years because I went right to industry to through my internship, and then I got a full-time job even way before I graduated. I graduated in 2018. It took me quite a little bit of time to finish my dissertation because I was a full-time employee. Before that, you can check my LinkedIn. I have a master in optics and also in physics, one from the University of Central Florida, another one from University of Puerto Rico. And going all the way down to my original roots, I actually started working very young, since I was a child, in my parents' farm, doing land work with coffee. My parents are coffee farmers, and I grew up actually planting the coffee plants, taking care of the coffee plants, and picking up coffee. And once we have the beans dry from the sun, sell it to the open market. So But for some reason, I decided I didn't want to be doing that anymore. It's hard work, and second, I wanted to do be able to do a greater impact. So I went to physics, optics, and metrology. But I don't know, if I think a little bit more seriously, maybe coffee has a greater impact than metrology. It impacts more people and gets more productive society. So I have to think about that statement of getting a broader impact. Anyways, let's get started. Size, in terms of numbers, we are a very global company. We have over 170 years of history. If we talk in terms of numbers, we have over 46,000 employees worldwide. The revenue in the fiscal year 23-24 was around 10.9 billion euros, and from that, around 14%, 1.5 billion, was invested back in R&D. And that's because size is not in the stock market, is owned by a foundation, and we are really committed into actually developing new products that are great for industry and research and academia and medical, etc. In fact, size is composed of 4 different segments: semiconductor manufacturing technology, industrial quality and research, which is where I belong, medical technology, consumer markets, optics, and photonics as well. And in terms of numbers, now specifically talking about industrial impact, this is the percentage of all the equipment that or the manufacturers that use size equipment. In terms of percentages, we enable around 80% of all the microchips worldwide that are manufactured using ASML lithography systems with size optics. And we have enabled 36 Nobel Prize winners that have used size devices for their scientific progress. And when the NASA Apollo mission went to the moon, we sent around 50 different size lenses to take the pictures from that mission. If I narrow a little more down to the segment where I belong, which is the industrial quality solutions, here are the numbers. Let me just point out this one, which is 64 size quality centers, excellent quality centers globally, and that will include soon a quality center that is being built right now, like 30 minutes away from here in Huntersville. And it's probably going to open in January, February. So it's going to be finished really soon. What is the history of the industrial quality solutions? Since we started making measuring devices around 100 years already, from the starting making calipers to the very first CMMs, and all the way to size Prismo, which you have one in this building, and other type of systems, size Metrotom, which is a computer tomography system, which is something I'm going to talk about. And you have another system down there, is the F25, is not in the picture, but it's also a very accurate CMM, coordinate measurement system. And of course, we have all the software capabilities to analyze the data. So a lot emphasis on size Calypso and size Inspect now with the acquisition of GOM back in 2017 or so. This is a question that Professor Raha has posed when I was trying to make the slides, and he asked, like, which metrology tools software currently used for dimensional surface finish, for dimensional metrology, form specifications. You already saw the portfolio. We use a lot of them. We are in the business of metrology. So we do from coordinate measurement systems all the way to laser trackers and surface finish instruments and X-ray, computer tomography for metrology and nondestructive inspection. So just let me give you an example. Let's imagine you have a casting part and you need to inspect that. So what kind of inspections you could do in that? And you see all the instruments that you can use. You can use software for design, simulation and validation. You can do a projection light to do a full field inspection. You could do X-ray to do 2D or 3D analysis of the inside of the part without actually cutting the part physically, so it's non-destructive. You can inspect the geometry with a laser scanner and do GD&T analysis, or you can use a CMM if you want the most accurate data. Tactile systems are still some of the most sophisticated in terms of accuracy. Or you could now start sectioning the part and do some material analysis in an electron microscope. And do a cross-process quality data where you correlate all the data that you have collected from that part. So there is a lot that you can do from dimensional metrology all the way down to material analysis. And since I'm going to focus on some of those instruments, I'm going mainly talk about X-ray and industrial X-ray microscopes. In general, this is an academic class, so I'm not going to be pitching the size systems. I'm going to talk in general about what X-ray technologies are. But here is the software that we use, most popular Calypso and Size Inspect. And this is some of the main instruments that Size does. This is the family of the X-ray portfolio that we manage. We are one of the leader manufacturers of X-ray quality solutions that include lab systems and production line inspection and metrology. My main experience has been with the Metrotom systems, which I did use to do my PhD dissertation, and now I am product manager for X-ray microscopy. So if I give you examples, my emphasis would be mainly on that. But don't forget that they can also be used for fast 2D inspection or kind of inline production, checking one part after another. Okay, let me be a little more academic now and go back to the roots and talk about the history of X-ray. So the history of X-rays start back in 1890 with the discovery of X-ray by Wilhelm Röntgen. And right after that, this technology started to be useful for medical diagnostics, because they can see inside of the human body without actually doing a surgery and cutting the body. So since then, we started to see differently. It changed the way we used to see the human body. And it was in 1970, so a lot of years passed before Gottfried Hunfeld in the UK created the first CT system that could reconstruct now in 3D. So right here is only 2D, just the projection of the X-rays, and here now you can see slices with the three-dimensional data that you can reconstruct from the brain or a tumor that you might have. And Alan Comark got also credit for some of the mathematical reconstruction theory about CT. They got awarded the Nobel Prize somewhere in 1980, I think so. And right around that time, the industry started to use this technology to inspect mechanical parts. So medical technology is a great application, but now we started to use it for non-destructive inspection to inspect defects inside of parts, like going to an aerospace or automotive to see if there are cracks, porosity, or even electronic components were inspected with X-ray CT. And around 2000, since around 2000, maybe late 1990s, people started to use this technology for dimensional inspection, dimensional metrology. And there has been a lot of research since then, including the 2010s, and I did my dissertation on dimensional metrology with X-ray computer tomography. And we can inspect all kinds of parts, including medical devices, electronics, automotive, or aerospace components. So going now to explain what the technology is, what CT is, it's quite simple in terms of concept. You have an X-ray source, and then you have a detector. You shoot X-rays. They go to be more effective in a cone beam. It could be in a line, but it takes a longer. If you send in a cone beam, then all you need is a stage where you place your part that is going to rotate when you collect projections before doing the reconstruction. And this is the way it is done in the industrial setup. The X-ray source is in a fixed position and the detector is in a fixed position. In the medical industry, they do it a little bit different. Because they need to put a person inside there, so the machine, the detectors, and the X-rays actually rotate around the patient. If they were to use this approach, then it would be the patient that rotates, and it would be a little bit annoying to do that. Plus, not very stable for the kind of quality imaging. But in industry, we can do that, and in fact, it's very beneficial when you do metrology to have a fixed source to detector distance. CT is not the only non-destructive technology. There are other technologies out there, including eddy current and ultrasonic testing, and they have some ability to penetrate inside of the parts, but X-ray is the one that actually can go deeper, and in terms of resolution, has better resolution than ultrasonic and eddy current. The only other technologies that beat X-ray, of course, is white light interferometry, but this has the great resolution. The disadvantage is at the surface. You can only see the surface. So X-ray, the main advantage is being non-destructive, seeing below the surface. And the resolution that you can achieve depends on the field of view, basically the size of the part, and also the type of technology. You might need to do some tweaks here and there. So we go from micro CT that see in millimeters to micro CT that can see resolutions in the micrometer, down to nano CT that can see in nanometers. And even there are way better technologies in terms of resolution, synchrotron CT, but then you need a particle accelerator to create these X-rays. And that's a big investment, so you need to own a national lab or something like that. And because it's very difficult to get a beam line, then Zeiss builds X-ray microscopes that allows to get a kind of this quality of data with a loud system. Those are the 3D X-ray microscopes. And in terms of kind of technology setup, the difference between those two is that the traditional X-ray CT is the flat panel, basically, and it's a cone beam projection. We could improve things, and this is the technology that gives push a little bit the limits of resolution, as you can add some optical detectors, so you collect with a scintillator the X-rays, and then you magnify them through a set of lenses, normal lenses, because the X-rays get converted into light here before to go into the CCD detector. But before collecting into the CCD detectors, you can pass them through a set of lenses and get higher magnification. This combination of geometric magnification and optical magnification allows you to see at a higher resolution. We call them 3D X-ray microscopes, because it's like in a line microscope we have a torrent that rotates, so you can switch to different lenses to get greater magnification if you want. Of course, it comes as a trade-off, as a cost of the field of view. The field of view becomes smaller and smaller. And I have an example here, which is very practical. Imagine you have a smartphone and you want to inspect one of the electronic components. Electronic board, and you can see this, put the board there and see inside as you're seeing here without actually destroying the board, because you can see all the slices after you get the reconstruction. And if you want to see at a higher resolution, then you switch one of those lenses and you can see now that you see details that you weren't able to see in the previous imaging. That you see now the porosity and some of the details of the connections of the vias between the different layers. If you want to do assembly inspection, for example, of the camera lenses, you can put inside the camera lens component and see everything, how the assembly of the different lenses are, and actually you could do some sort of dimensional inspection here by checking the dimensions, the diameters, and the curvature of these lenses. And something that is very popular nowadays is the inspection of batteries. Batteries have become a very popular topic of research with the new energy vehicles, electric cars. And this is an example of inspecting inside of a battery that has been cycled after several hundreds of charging and discharging cycles. In fact, so you can see the degradation of the particles and some traces of delamination in there. Okay, so all good. Yes, we can scan all different kind of parts and take great imaging. But I know there is a great focus on dimensional metrology in this department or in this center. So the question is, okay, can I do dimensional metrology with CT data? And this is a very fundamental question, because someone very naive that doesn't know about metrology could say, oh yeah, don't you see the scale bar over there? Yeah, well, if you're a metrology person, then you start asking how accurate is that? And what's the uncertainty of that measurement? Do you have an uncertainty value associated to that? So that's where the metrology thinking comes about, and then you have to start asking deeper questions. So how well is the reconstruction? The voxel data represents the actual dimensions of the part, because you are seeing a virtual reconstruction. No, you're not touching the part. You are working on a computer software. And the answer to do that, can we do metrology? The answer is yes. We have a long experience doing that with the Metrotome line. In fact, that's why we call it Metrotomes. It's computer tomography systems for metrology. In this case, I'm going to show you one example how to do it with a 3D X-ray imaging system that was in the design from the ground work for metrology, and this is the 3D X-ray microscope. This is something I did when I joined the company, and there is a type of artifact that is very popular for CT calibration, which is a multisphere phantom. And you can calibrate that multisphere phantom very well with good traceability and measure it with a CMM and know the distance between the sphere. Now you can put it inside of the system, and if the system is well calibrated, or if you need to do corrections, you can do them, and then you can measure that and verify against the calibrated data. So basically you calculate the deviation from CMM. And after we did the corrections that were needed to do with software, after studying the system, we were able to verify that the system would give us deviations from calibrated data below 1 micrometer. And the calibration of this is a small phantom that even fits in the tip of a finger, was made at the National Institute of Metrology, in this case METAS, which is the National Institute of Metrology of Switzerland. And this is the maximum permissible error that we got for that kind of calibration, which you probably are familiar with the type of calibrations for CMMs. Maximum permissible error is in the same time of order, or at least form, 1.9 plus micrometers plus L over 100, where L is in millimeters. We've done this for other systems. The Metrotome systems have bigger phantoms, so you can compare the dimensions of the phantoms, and all of that has been certified with the different types of institutions in the European Union. So I don't need to go all deep into that. I just want to mention again the size of the phantom in this case is targeting very small parts that fit in the 5 millimeters field of view. The Metrotome is able to scan larger parts, but in this case for metrology we designed it just for using one of the lenses from this X-ray microscope. And all of this is well documented in one of the publications in Measurement Science and Technology. So you can go there and check. When you talk about metrology, it's not just about accuracy. You need to also compare it against about it's not just about comparing about more precise or accurate system, it's also checking the repeatability. So if you measure the same parallels, the same distance over and over again, do you get the same result? And if you get some dispersion, how big is that? And you can see that we did that with 3 different systems, actually more, but trying not to overload the data here, we plot 3, and you can see how the repeatability is. If you look at this length measurement, this is 3.604, this is in millimeters, and this is 3.606. So from here to here, there is 1 micron, and you can see that the repeatability is below a micron. And yes, there are changes between one system to the other, and that's due to environmental factors, different locations where those systems are. The workflow is here, and some of the ideas of the geometrical corrections or scaling that you have to do in the detectors. Again, I'm not going to go into details. You can read the paper, but the main idea is that once you do this, then you are all good to do GD&T on those measurements in the actual data. What happens if you don't do the corrections, if you don't figure out how to do these corrections in your system? Well, this is data when the system has been corrected, is really good, well behaved. If we don't correct, then you can see that the uncorrected data is in this tilted line in blue, and you can see that there are larger deviations. So what this calibration is doing is correcting for that, is accounting for that. So that's why it's very important to do so. Otherwise, you might have discrepancies when you are trying to do GD&T because your measuring instrument is not calibrated. So we went from doing 3D X-ray microscopy or 3D X-ray imaging to do dimensional metrology now in a set of data that you can read in the computer in 3 dimensions and do some type of 3D reconstruction. And the applications are several, including camera lenses, small plastic components that goes into connectors, or even fuel injector nozzles. And this is really a nice example, not only because you do dimensional metrology, but you can see other types of non-destructive inspections, like you can see inside of the part the roughness of the internal surfaces, and also some of the porosity. If you try to do this with a tactile system, it's really, really hard because you see the dimensions of the holes. The holes are in the order of 200, 300 micrometers. It's very difficult to get inside with a tactile system. And those are some of the innovations we have done and we are able to do, but we've done a lot. This is a little bit of the history since we started dealing with 3D X-ray microscope. This was an acquisition from a company in the California Bay Area, which it was called X-Ridia. And we've done all of this innovation, including the latest, which is deep learning algorithms to improve the quality of the reconstruction and reduce the scan time by reducing the number of projections. But that's a different topic. It's very interesting. You can read about it. There are some publications out there, but that has been a very successful product. If we move back to the instruments that were designed for metrology, they are the Metrotoms. There are different models, and they are all listed here. But it's not just about doing the systems, it's also doing the software. So we have a couple of software, Calypso, that you use, also have licenses in these universities to train the new generation of engineers, but also Size Inspect, which is now the newest software we are using for X-ray inspection and for other coordination measurement systems. So getting now specifically into the metrology systems, you can see how you can do from metrology, non-destructive inspection, material analysis, assembly control, reverse engineering. And the reason why I'm doing this presentation this way is because now I'm getting into what I did for my PhD dissertation, which I used a metrology system from Zeiss. And the architecture of those systems is basically a well-calibrated system in terms of the axis movements, and the source to detector distance is in a fixed position. It doesn't move on purpose, because if we have good traceability of the distance, then we can get a really accurate idea of how the reconstruction of the voxel size is like reconstructing pixels in 3D is for the reconstruction of the part of the reconstruction in 3D once you have a virtual kind of model of the part. So you can now do the GDMT without worrying so much about is this calibrated data or not, because the system has been designed from the base to be a metrology system. When we talk about all X-ray CT competitors out there, size dominates in terms of the metrology market. Most of the other companies create just NDT systems, imaging systems, not metrology systems. So that differentiates us. And I actually studied those systems very well when I was doing my dissertation here back. I started in 2012. So I started looking at all the influencing factors that go into the measurement. What influence the dimensional measurement of a CT? And those are environmental, operator, the object itself, data processing, and the CT system. And the workflow again is here in terms of dimensional metrology workflow. You get the part, and this is actually a frustum artifact that was manufactured at NIST, and it has internal features. Once you scan and you get projections, you get an interesting face there. It looks like a winking, smiling face. But in reality, it's because you are cutting with a virtual projection that is in a tilt position. Once you reorientate the axis, then you can see that there are a couple of holes that are in a conical shape. And once we did the measurements, we were able to compare with CMM data, very well calibrated data collected at NIST. And that was the initial part of my dissertation. And I have been talking about CT, but it actually, this technology back in the days, and maybe some people still call it CAT scan, like when you go to the doctor. And it was quite interesting because I had a cat, and my cat just stayed with me during my X-ray CAT scan dissertation. She's looking at the image of the part. X-rays, some people ask, well, is it dangerous to work with X-rays? Not really, the cabinets are very secure, but the only thing I tell you is please keep the cat outside of the machine. If I were to do that, my wife will kill me, probably. And this is a little bit of the data I collected in the NIST artifact, and also an additional artifact we built ourselves with some carbon fiber stems, but they kind of tilt. So it also shows that CT is not only good for internal features, but also for parts that are flexible, like plastics. Maybe it's not very good for a CMM. The CT doesn't put forces into the part because it just sends X-rays, so it's also a great advantage. Here are some of the deviations from the nominals. I have data later on collected with CMM comparison. This was my paper number 1 out of my dissertation. And it's been a really good, it's becoming a classic paper. It was awarded as the editor's choice paper of quarter 1 in 2019, and I think it already has close to 200 citations. I had to write also a literature review, so that was paper 2, and paper 2 basically talks about a little bit of the history of X-ray CT, the projection in terms of use in markets, in the automotive, medical devices, aerospace, and a little bit of the difference with the technologies. Tactile is a great technology, it's very accurate, but it also suffers of shortcomings, like if you have a very rough surface, then you're passing a mechanical filter. You would have to change the size of the sphere that you are using for the tactile profiling if you don't want to get a very high mechanical filter. But still, you're still dealing with a mechanical filter unless you have a very smooth surface. You can opt to use optical systems, optical CMMs, laser scanners, and then you see a little bit better. but then you don't see inside, and you're still dealing with pixel data. In X-ray CT, we also deal with the pixel or voxel data in 3D, pixels in 3D, with the advantage that now we can see inside. So that's the main advantage of X-ray CT. This was a great review again, very fortunate to get also the editor choice for that, my second paper, which I think it has close to 300 citations right now. So it was really great and very fortunate to get those publications out from here, from the University of North Carolina. And this is part of that. I review the different types of approaches that people are or were using at that time for uncertainty assessment of CT. Again, we not just care about measuring, we need to make an assessment of the uncertainty of that measurement. And there were at that time several international comparisons. I have 3 in here and show where the type of uncertainty estimates for the different measurements in terms of size dimension was for the different comparisons as compared to the traditional uncertainties with CMMs, which are quite low. So CTE still have larger uncertainties, and that tells you that CMM is still a very mature technology. For more than 50 years, people have studied those systems to get those uncertainties very down to 1 or below 1 micrometer, depending on the system you're using. The paper number 3 was about creating amplitude wavelength maps for X-ray CT systems. I was at Professor Raha's office and actually saw the classic paper about amplitude wavelengths sitting in his desk. And I used that theory to create some maps based on the resolution of the systems and the scanning range. And it's also interesting, I worked with Dr. Stuart Smith. He was working with Jeff Towson at the time. They designed this artifact. You can see the logo of UNCC there, basically to be able to inspect the resolution of CT systems. So based on several measurements I did, I create those maps. The theory, you can read it in the paper publication, but basically I compared where CT sits in terms of surface wavelength, or think about like resolution against amplitude, maybe scanning range, as compared to optical AFM, which is very high resolution, as you can see. The size dimensions are smaller, and CMMs that cover a very large range. I'm talking about all the technology, CMM technology in general. And CT sits around there. The original paper had a little mistake in one of the slopes, so there is a correction in a later on paper. But this is the corrected data, and I did plots for different kind of KV. KV is the energy that you put into the system to shoot X-rays. So basically, more energetic X-rays come out as you increase the KV to pass through the part. And the more energetic, if you use a 450 kV, then the larger the part you can penetrate, or the denser the part. So those are plots in terms of scanning range and also resolution. If you increase the kV, as you can see from the dotted line, then the resolution decreases. So there is a trade-off between higher energy systems and resolution. They don't go together. And if you want to see what happens if you scan different types of materials like steels or aluminum, then that's an amplitude wavelength plot over there. The fourth paper was about seeing the different methods of uncertainty estimation for CT. And there are different methods, and you probably have already heard about making sure that you are including random uncertainties or systematic uncertainties, and you have to add those up. And then there are different ways to try to calculate that, root square means, and etc. Some of them even proposed by NIST. You can check the paper. I'm not gonna bother you with explaining all the details, but the main idea is I took that custom artifact from NIST, checked different types of features, and calculated with those different methods the uncertainty, to see where they sit at. And that's the plot that you see there. So you see what the different systems estimate, if they overestimate or underestimate, and the idea was to show the different influencing factors. In fact, I studied how the temperature inside of the system changes when you switch the X-rays on, and then you count the time by putting sensors. One, the red one, is very close to the X-ray source. The other one is outside of the CT scanner, and the other one is at the center of the rotational stage. So you see that the temperature changes very differently. 20 degrees was the room temperature of the CPM lab, so this is pretty good outside, but in the inside there is an increase in temperature. And if you want to do serious dimensional metrology, you have to compensate by that. But you also learn from here that if you start measuring the part too soon, you might be in the transient state, and that causes problems for you because you start measuring the part, and when it finishes scanning, the temperature went higher. So you have different dimensions there. So ideally, you have to wait for the more stable region of temperature to do your measurements. So that was a really nice learning, and if you know the temperature because you have measured, then you can compensate that. This might not be a big deal for scanning steel parts, but it can be a problem for plastic parts, which have a very high coefficient of expansion, as you can see there, 126 parts per million. And this is the type of errors that you can get without compensation or after compensation. So this is the correction. The red part is after you correct the deviation from CMM data. I did that with an aluminum part, and you can see that because the coefficient of expansion is smaller, we also have a more stable kind of data. The deviations are smaller. The next paper, paper 5, was about let's start looking at the different factors that influence the measurement. And in this case was the number of projections. As you hear at the beginning, you put the part starts rotating, and you collect projections. And in reality, you have to collect more than 1,000 projections to get high quality data. This is a peak signal to noise ratio. So if you collect less than 600 projections, there is a low signal to noise ratio. You have to collect more than 1,000 projections to be able to get a really nice high quality data. This is great, this is very insightful, but the question that I had in my research is not about the quality of the image, it's about the quality of the dimensional data. So what happens if now I calculate the deviations from CMM in the data by changing the number of projections? And you can see how it changes depending on the type of data that you are collecting. If you are taking measurements of form, they are greatly affected by the changing of projections. If you are collecting the, measurements of distance and probably good distance measurements, then they don't get as much affected. And that's because in this case I was taking measurements, let's say from the center of one hole to the next one, and those distance take advantage of averaging data on a series of voxels dimensions, and that kind of average the errors, and then you get this compensation in the distance data. And you will see that in other types of data analysis that I did. The next paper was about, okay, what about if we change the orientation of the part? So when you have the part, you can put it like here, or you can tilt it. And in reality, tilted seems to be advantageous, because if you put it right vertical, you get cone beam artifacts in the top and the bottom. So basically, the surfaces that are flat, almost parallel to the X-ray beam, get really affected in the reconstruction of the data. And that's pretty well known from imaging perspective, but from dimensional data, I didn't know exactly the problem. So we designed this type of gauges. We measured with a CMM, also used the same software, Calypso at that time, and compare using Calypso in the CT data, tilting that part at different angles. And you can see that you should avoid this type of angles from 0 to 10, or maybe after 50, because that's where your higher deviations are. Ideally, you should tilt the part for this type of dimensions between 10 or 30 degrees. And we also verify that with simulations that take into account the projections. So we compare the actual real data with dimensional data. Of course, dimensional data is faster to generate. To be able to generate the actual experimental data, it took a lot of scans because each one of those dots represent a different scan, which takes in the order of several minutes. And this is an artifact, a metal artifact that was designed by the Metrology Institute of Germany, PTV, and they were generous enough to loan that to us. And I took measurements with one aluminum one and a steel one, and you can see that it's the same type of thread. And I did mention that unidirectional lengths or center-to-center length or diameters don't get as affected as measurement of roundness or point-to-point bidirectional length, and that's what you see there. This is a roundness measurement. It gets more affected than the diameter or the bidirectional length. And all of the reasons why it's explained in the paper. There is the next publication, which was also from the dissertation, which is, okay, good. Now we understand that we have to tilt the part. What about positioning the part in the cone beam? And that's changing the magnification. If I change the magnification, does it affect the dimensional measurements? And the data that shows here, it shows here for a voxel size of 8 micrometers and 20 in terms of imaging. You can see that you get a little bit of a smoothing kind of data when you decreases the magnification. So this is a higher resolution. But the question is, okay, what happened in the dimensional data? You can see that not much happened to the unidirectional lengths, which is basically center to center of each hole measurements compared to the CMM. These are the different magnifications, and the data all is clustered below 5 micrometers. But the point-to-point data, which is basically collect one point in one of the edges and another point there, of course, you have to determine very clearly where to measure in the middle of the plates by creating a reference in the top and the bottom, find the middle. That's how we did with the CMM. And if you do with the city data, then what you get. And now you can see that if you change the magnification, you get a larger deviation from CT data, from CMM data, negative in this case. So if you plot now in function of magnification, this is what you get. No big deal for uni lengths, but all the other type of measurements get affected by the magnification. And I propose to, instead of using the typical CMM maximum permissible error of a constant plus L over K, add an additional term that is called the magnification axis over a constant. So that was the next contribution. The very last one, I think, is about thinking now if we affect the part by surrounding it with material, thinking a little bit of internal features, does it affect my data? And it depends. We generated different kinds of enclosures with kind of geared shapes or threaded shapes. And you see here a little bit what happened with no shell and plus shell. There is a little bit of noise. Again, I was interested in the dimensional data. This is a steel part in this type of shell. You can see kind of a linear type of effect in terms of the deviation from CMM. This measurement is ordered from the center, so the numerals represent the greater the number is the farther are you from the center, so they kind of get a distortion effect. And if you want to do serious metrology, you will have to correct for that. But again, the most affected are the bidirectional lengths. And we did that with an aluminum artifact. You can see that now these ones don't get as affected. Neither the diameters in the mid-planes are within the 4 microns, but the bidirectional lengths are the ones that suffer the most I did that with the multi-sphere phantom, and you see similarly that the sphericities measurements of form are the ones that suffer the most in that type of measurements. I think till here is what I published from my UNCC. Again, I have a full-time job, so I stopped publishing, and there has been a paper that has been sitting for more than 3 years in my desk, and I just took a look more recently that I have more time, so this is under review. It's more looking into, if you do multi-laboratory comparisons, and you have different inputs with different uncertainties that they calculate from different ways, is there a way to have a metric that that's the metric that I choose to compare those laboratories, affect my assessment? So I do comparisons based on Monte Carlo simulation and some of the analytical formulas to do that. It's gonna come out soon, hopefully. That's all I did for my dissertation. I have been keeping active on collaborating with some universities in Spain. This is and in the US. This is a nice application to additive manufacturing, drawing on into metrological concepts now to calculate porosity, see if we classify porosity in additive manufacturing parts, and if we can do some kind of dimensional characterization. The next one, the collaboration, is in terms of calculating different types of thickness and through-hole detection. You can read the references. This was already published, and you can see the variation of thickness as opposed to the through holes in terms of the linear energy density of the additive manufacturing component or machine that you're using. So you see lots of applications. Going back to the 3D X-ray microscopy, this is the workflow also that we kind of illustrate in one publication in the Journal of Nondestructive Evaluation. Collaboration with the ORNL for non-destructive evaluation or multi-scale characterization of additive manufacturing parts. Changing application, I mentioned batteries, so this is another reference for scanning batteries and what you can do and correlate with electron microscopy or SOP, which has higher resolution. Or applications in medical devices with X-ray CT is very popular. Because it's simple, it's just scanning for assembly inspection, but it also for metrology. People like to scan the dimensions of those devices. Or if you use X-ray microscopy with the set of lenses, then you can go all the way to scan pharmaceutical formulations. This was at a conference presented at a conference recently in February 2025. I have shown this image. So you can scan electronics, and this is the workflow for scanning electronics components. So you can see that really X-ray CT has application not only in dimensional metrology, but it has a multidisciplinary kind of application from assembly analysis, electronic inspection, porosity analysis, part design analysis, metrology, structural assessment, aging analysis of batteries, fiber materials, and I have restricted myself to industrial kind of applications. Outside of this scope, there is oil and gas, materials research, there is plant analysis, there is life sciences where you scan bones or you scan brains of animals or stuff to do all kind of studies. So it's really a fun field to work in. Now going back to what we do as ICE, we serve all of these markets that I already mentioned, all the way to life sciences and oil and gas. So we really serve at sites industrial quality solutions, all type of industrial sectors, from parts that are made by machinery, aerospace, electronics, new energy vehicles or electric cars, power and energy, medical, and metal products. So it goes back to that very first slide where I showed how much of impact we have as a metrology company into, or in general as an inspection, industrial quality solutions to the different industrial sectors. So with this, I think I'm just right on time to allow you to ask some questions. Again, I used to call this CAT scan.
CAT scan, okay. Thank you. One more general question before I.
Yeah, yeah.
You know, you said you traveled to Asia, Europe, and US. So what's your sense of the metrology, attitude towards metrology in these different continents? And then in terms of technical people within the company, do you see any big differences?
Yeah, Europe is very mature in terms of metrology capabilities. In fact, when you look at the names of the manufacturers of metrology equipment, most come from Germany or Switzerland or European companies, not so much from the US. So Europe, the regulations in terms of metrology are great. In the US, there is a lot of interest, but it's driven by regulations. So, for example, in the medical industry, where the FDA has a greater impact and puts a lot of emphasis in the safety of the patients, then yes, GD&T is very heavy. And also in aerospace companies that are safe critical. But in terms of manufacturing metrology equipment, Europe has the lead. China or Southeast Asia, Japan has been a great focus. In fact, you know a little bit of the history. If someone told you US had the lead in terms of automotive back in the 60s or so, until they kind of weren't creative enough in terms of the standards of doing manufacturing, and then Japan took the lead back in the 1990s. That's why Japan is so heavily in automotive, and they actually brought a lot of metrology engineers from different countries, including the US and Germany, to help them with these standards of quality.
What do you see in China?
There is a lot of development of electric vehicles. So it's more than 10-20% of the cars on the streets are electric cars. So they have the lead.
Any questions? I mean, you covered a lot, so.
Question.
Yes, please.
This might be naive, but you emphasize the advantage of X-ray CT is being able to inspect the inside of a part, and that includes inspecting assemblies. Are there situations where being able to inspect an assembly when it's all put together can actually replace the inspection of individual parts prior to assembly?
Yes, in fact, that's what people do with a lot of plastic assemblies. X-ray has great advantages, but it also has some trade-off. So if you have different components from materials that change a lot in terms of density, for example, metals inside of plastics, then you might suffer of something called metal artifacts, and that decreases the accuracy of the dimension measurements. So CT is a great inspection tool for assembly analysis. It all comes back to what are the tolerances you're checking. So if your tolerances are in the order of 20-50 microns, it's a great first inspection technology from assembly products, and it replaces your inspection with CMMs. But if you care about dimensions that your tolerances are below the 10 microns, then CMM still is the best technology.
Makes sense. Thanks.
What is the typical difference in precision between your kind of single part or single assembly X-ray machines versus your ones that measure each part in a product line?
Yeah, so let's talk about technologies, and it doesn't depend on who builds it. In terms of technology, the uncertainties of tactile systems, CMMs, or the accuracy, if you want to talk about maximum permissible error, we're talking about single-digit micrometers. And in fact, some systems like the Mikura, well, you don't have it here, but the size Mikura can go to 0.7 microns maximum permissible error. So it's very accurate. You cannot do that with CT. CT, the uncertainties, you saw a lot of my plots, they are in the order of 10 microns or even higher. If you were to use laser scanner, which is also a great technology, is in between. Laser scanner is great because it can see the outside of the part, it cannot see inside, but it could be faster, it gets you more data, but the uncertainties, when you read the literature, are still in the order of 8, 10 microns or even higher, depending on how fast you measure the point clouds and all of that. So in the tens of microns. So CT is always going to be, until now, the reference. And that's why all the data I collected was compared against CMM, because that's my golden standard measurement instrument.
I have two questions. One's an easy one and one's maybe more philosophical.
Okay,
My first question is, what's the cat's name?
Lily.
Okay, wonderful. My second question is, it seems to me that you've done something that constantly haunts me as a wannabe metrologist, and that is to compare and contrast uncertainty analysis.
Mhm.
It's sort of a taboo subject for some people.
Yeah.
So my question for you is maybe more of a philosophical one. How would you assess how good an uncertainty analysis is, or how good an uncertainty number is?
Yep.
Everybody sort of calculates it differently,
Yeah.
and they include different things.
Yeah.
But when you look at one, what is your first gut reaction for how good is it?
Yeah, so the first thing I look at is okay, is there a component that accounts for randomness or like the random errors that gives you an idea of the repetibility? And a very first number is the standard deviation. You measure several times and you calculate a standard deviation. So how good is that? That gives me an idea of how repeatable is the instrument. The second one, which is the more systematic, is okay, was that accounted for, and was in principle the best way to calculate the uncertainty? The ISO standards say if you know the systematic error, you have to find a way to compensate for it, correct for it, and once you correct, then you account into the uncertainty. In the old times, 10 or 20 years ago, you would include your bias. If you know your bias or an estimate of the bias, you include the bias, but that increases your uncertainty. The new guidelines say, no, you correct for the bias, but you still have an uncertainty of the bias. So now you include the uncertainty of the bias on that. So what gives me a good feeling is on the number is how careful was the metrologist in accounting for the different factors. Is they just throw me a number and there's no clear explanation, then I become suspicious. And if they give me a standard deviation, fine, but that only accounts for repetibility. How they accounted for all the other factors, bias, correction, temperature, environmental, and all of that.
Thank you.
Fascinating presentations. I have multiple questions. I can go all night. So the first easy question that I have is like, how many hours did you work in your how many hours did you work like while you were here at UNC?
Oh, a lot. I was down in the lab from I don't know 8 and 9 a.m. till 9 p.m. or so. So I work a lot, but I also stayed here for a very short period of time. I came in 2012 and I left in 2014, 2015. So my greatest concern, I knew that the system that they put in that lab was alone. The university didn't own the system. So my time window to collect data was limited. Initially it was 1 year and they extended to 2 years, but I knew how limited amount of time. And then after I collected my data, I started working full time, so I had to work at night to analyze my data on weekends. But it's all, I reflect back, it was a lot of effort, but it paid back. I have a good job with a nice company, and my work got some attention, so it's worth the effort. Would I repeat it? Probably not. I know PhD life is very hard. You put a lot of hours for little pay, and you have to sacrifice a lot in your personal life. But it pays in the long term. So that's what you have to have in your mind. Just think in the long term. And the great advantage is that you are still young, so you can do that. If you, because you start growing old and it's harder to do that. So if you want to work really hard, do it when you're young, because it's gonna become harder and harder.
You focused a lot on dimensional metrology part. So what do you think of using CT for surface metrology? What do you think is the state of the art is?
Yeah, it's a challenge. Some people have used for surface metrology in some universities in the UK. There are a couple of references that you can read on that, but there is not much. Mostly it's coordinate measurement metrology. Surface finish, the problem is that the data, once get reconstructed, might hinder some of the roughness. So you have to be very careful. So though it's possible, it's not the best application. And also, you mentioned the focus on dimensional metrology. Nowadays, I don't focus as much as I did when I used to work with the metrotome. Now I work with the X-ray microscopes, and you have to widen your horizons. When I was here at UNCC, I was thinking on metrology, and I thought that the world was all about metrology. I went to the industry and I discovered that I was living in a bubble. I mean, it's great, it's beautiful, and it's complicated. Metrology is complicated, but when you see the application, the market for X-ray CT, only around, I would say, 10% is metrology. The other 90% is non-destructive inspection, because people just want to see inside of the part if the process went right or wrong. In the case of a battery, aging of the battery, they are not measuring that like dimensionally. They're measuring other things. So it's good to widen the horizon, especially when you're so focused in a topic of research that is small and you think everything goes around that.
Okay, in the interest of time, I think we'll let thank Advanced again